Welcome to today's lesson. Today we will find the inverse of linear functions and we will be able to explain how to find the inverse of functions. So let's take a look at today's lesson. Let's take a look at today's do now. Answer the following. You have two questions in which you want to determine if the following is a one-to-one function. So I'm going to let you guys pause this video and do these two on your own. All right, so for number one, we can see that f of x is not a function because the domain repeats. The fives are repeated twice. Therefore, since it's not a function, we cannot find one-to-oneness. Number two, we have g of x is a function, looking at the x values, right? Looking at the y values at the range, we determine that it is a one-to-one function. So let's look at today's thinking. What is an inverse function and how do we find it? So inverse functions. An inverse function is a function that will undo anything that the original function does. If a function is not one-to-one, it does not have an inverse function. Super important. We can find a function's inverse three ways. We can look at it numerically, graphically, and algebraically. If we're focused on the algebraic piece, I have the steps here. Write the function in terms of x and y. We will switch the input and output, which means switch your x and y's, solve for your new y, and write your answer using proper notation. So what is proper notation for inverse? If we have our function f of x, if we are finding the inverse, we would say f inverse of x. That little -1 is not an exponent, it's inverse. So let's look at example 1. Given f of x, x over 2 plus 3, we want to algebraically determine if f of x is a one-to-one function, and then we want to numerically find f inverse of x. So in order for us to do part A, we need to determine if f of A is equal to f of B. So we're testing and trying to get A equals B. So we're going to solve. If I move 3 over, those 3's will cancel out. And at this point, if I multiply both sides by the reciprocal, the 2's will cancel out, leaving me with A equals B, which is good, which tells me that we do have a one-to-one function. Since f of x is one-to-one, we can go ahead and find the inverse. All right, so how do we find the inverse numerically? When you are asked to numerically find the inverse, what you need to first start off doing is find points for the original function. So we're going to use our calculators and input f of x. Okay, so I did that. I went to y equals, I've input my function, and I'm going to get my table, second graph. Within the table, I am going to pick 4 points. Any nice points will do. Nothing with fractions, nothing with decimals. So I'm going to pick 0, 3, 2, 4, 4, 5, and 6, 6. So that's the original function. Now that I have the original function's inputs and outputs, what we are going to do is find the inverse. So I'm going to create a new table with the inverse notation. The awesome thing about inverse is that the x's and y's, the domain and the range, switch. So if my original point was 0, 3, my inverse would be 3, 0. If my original point was 2, 4, so each of these y values are going to be my new x values. And each of the original x values are now my new y values. And this is the inverse numerically. So if they ask me to numerically determine the inverse of a function, all I need to do is look at the calculator, get some original points, and swap the x and y. Switch the x and y's for my numerical inverse. Let's look at example number 2. Finding the inverse graphically. So here we have given the graph of g of n. Graphically find the inverse, g inverse of n. So first thing I have to determine is what am I looking at? I have a line, I have a linear function in which it is a function and it is one-to-one. Doing the graphic test, I need to first start off We're going to start off by plotting the line y equals x. This is known as the reflection line. So this is the line that my original function will cross over, creating the inverse. So what is that line look like? It goes through the origin and it just has a slope of 1. So I'm just going to get myself some points here. Anytime you graph this line, you do want it to be a dashed line. And I'm always going to label it. So this is my y equals x line. That's my reflection line. So how are we going to find the inverse? What we do, right, just think of this numerically. What happened to each of these points? The original points get swapped to the other side. So what I'm going to do is all I'm going to find are some nice points within my line. All right, so these are some points that I identified. So I have the point here, 4, 5. This point is going to change to 5, 4. So it's right here. Okay, another point I found was the point 1, 0. That point is going to go to 0, 1. Another point I found here is -2, -5. That point is going to become -5, -2. So I have my 3 points here, and I'm going to connect those points. And this is g inverse of n. Each of these points have been swapped over that reflection line. That's why that reflection line is very important when you're graphically determining or finding the inverse. All right, the last one. We are going to do the algebraic piece. So for question 1, we have our function f of x. I see it's a line. We want to start off by determining whether it's a one-to-one. So I know that all linear functions are one-to-one, but algebraically showing this, we're doing that f of a equals f of b. Slowly getting a equals b. All right, so we knew this already. F of x is one-to-one, but there's my algebraic proof. Part B wants us to go ahead and find the inverse. So I am going to do this algebraically. So I'm going to start by writing the original function in terms of x and y. Then I'm going to change the x and the y. And our goal is to solve for our new y. So I'm going to move that 8 over. To get y by itself here, I would multiply each side by 2. And we would get 2x minus 16. I am going to write my final answer in proper notation. So don't leave it in terms of y and x. Change it back to the original function notation. So we have f inverse of x is equal to 2x minus 16. That is your final answer. All right, let's do it again. Here we have the same kind of process. We have our function g of a, algebraically determine if that g of a is a one-to-one function, and then go ahead and find the inverse. So part A, I'm going to let you guys try. All right, so here is our proof. G of A equals G of B. I plug in A, I plug in B. I slowly get this A equals B by moving that negative 10 over 3 on both sides and then multiplying by the reciprocal, which would leave me at A equals B. The next thing we're going to do is the algebraic piece. So we're going to find the inverse. We're going to start off by just rewriting the original function in terms of x and y. Once I do that, I'm going to change my x and y. And I'm going to solve for my new y. So I'm going to move that fraction over. I'm going to multiply by that reciprocal. All right, so I do that. I distribute that fraction to everything inside my parentheses, and I end up at this new updated function. I'm going to write my answer using function notation. So here, be very, very careful. We have a g inverse of a, which means that my input is not an x, is an a. So instead of negative 7 over 2x, I'm going to write negative 7 over 2a minus 35 over 3. And that would be our inverse for this problem here. So that is all. Keep learning, keep growing, and I will see you in our next video.